It's too big. All right, most of you are there. Let's see, there was an email. All right. There was an email from Matthew asking a question about the first project, but I'm not quite sure if everybody has the same question. Hold on a second. I'm trying to get my screens here under control. Are there any questions besides the question from Matthew regarding the use of the Sahil criterion? Alex says, I'm having an issue with getting small high hill values even if n equals 1 and m equals 1. Okay. Mohan has the same issue. What kind of numbers are you getting? 0.1. All right, there must be something in the units that we may have messed up. Can somebody send me what you're doing? Boron epoxy is a pretty strong material. Do you think we mix the elastic properties of one material and Okay. It is possible that I may have picked up the strength properties from one material and then the elastic properties from another material, which will be, of course, pretty bad choice. I will have to check on that. I'm not quite sure right now why the difference is so big. That I was under the impression that single ply will not survive the loads that I prescribed. Did I specify 100 NX to be kilo 100 or just 100? 100 kilonewton. Okay. All right. So that's not the issue. Then it is possible. So when you use 1000 for NX, you get something more than 1. Yeah. When n equals 2 and m equals 2, then you're going to 4-ply. Okay. In that case, maybe there is even a reason to make it 2000, so that we'll have a little bit more flexibility in terms of the laminate design and how we can. Well, I have to see the numbers. I haven't solved the problem myself yet, so I take this that you guys are doing the right things and getting those numbers. So I'm going to suggest that those of you who are having this, increase it to 1000. Let me open the file and look at the numbers myself, and we can start making the changes. All right, so let's see. This is 200 gigapascals. Yep, it's a pretty strong material. And these are megapascals. All right. Tension, compression to 2500, tension 61, compression 200. All right. One thing that you need to be careful about is this X tension, X compression, and Y tension and Y compression. If you look at the cycle equation, in there, you actually need to change the XT and XC depending on the stress state that you have. What I mean by that is, let me show you the equation for it, and then we'll go from there. Let me make this a little smaller and put it on the side. In this cycle, this shows both X and Y to be tension, assuming that sigma 1 and sigma 2 are both positive. If sigma 1 is not positive, if it's compressive, then compressive value should go in here. If this is compressive, compressive value should go in here. And depending on one of these, you may actually, instead of xt square, you may want to use x1 tension, x2, and write this xt times xt and change the x value depending on one of the x values, sigma values that you see here. So this is, I don't think I've used the Sci-Hill program in my tutorials, but this will be for you perhaps to check if Sci-Hill that I wrote, either I gave you the program file the last time, or you may or may not have this in your program files. So let me open that file and show you what I mean. Mathematica, open recently. All right. Okay, so 1,000 is a good value, Alex. And n equals 4 and n equals 3 seems to be reasonable. I want you to do something for me and look at the file that I'm showing right now. This is the program file CLT 2021 version 3. But the version that you guys have may not have this function right now. Which is called plot Sahil envelope. In fact, this doesn't work yet. Plot doesn't work yet, but Sahil failure. This Sahil failure, let me show you. Oops. Copy this. Next. Given the stress state in principal material directions, so you provide sigma x, sigma y, 2, sigma 1, sigma 2, tau 1, 2, material principal directions stresses, and then you give the entire 5 values of the x's, and the module computes the Sahil number. And give you back that number, and this is the function that does that. And if you see this, you check sigma 1, you check sigma 2, 1 by 1. If sigma 1 is greater than 0, if it's positive, then you check sigma 2. If that's also positive, you put tension, tension, and S. If sigma 2 is negative, then this is tension, sigma 1 square xt square, sigma 2 square y c square instead of yt square. And then if sigma 2 is greater than equal to 0, then you check again. So if sigma 1 is not greater than 0, that means it's compressive. You check sigma 2 again. So sigma 1 is compressive, sigma 2 tensile, and xc square. Actually, I didn't even do what I'm telling you in terms of checking the sigma 1 and sigma 2 and splitting this. Some people do, some people don't, but I think it is better that if sigma 1 and sigma 2 are two different values, sigma 1 is positive, sigma 2 is negative, then you should do this actually xt and xc. That is something that I just so sigma 1 positive, sigma 2 positive, sigma 1 positive, sigma 2 negative, and then sigma 1 is negative, sigma 2 is positive. I will again make this xt, and then both negative, sigma c squared. Okay. I think this is the best one that I have. So I'm going to put this version, load this version up again, and this should compute the Sahil number for you. And you can check your own subroutine as well with this one. I'm glad we wrote this discussion, because I was doing this, I think last week I wrote this. And right now, actually, I'm trying to make a plot of this Sahil envelope. And it becomes complicated to make the plot. And I'm stuck in there because I need to almost use piecewise functions to make the plot efficiently in one go, in one call. So plot Sahil failure envelope is not working right now. I'm not sure even if I, let me see if I wrote the function for it. I mentioned here, plot Sahil envelope, copy, paste it here, Sahil envelope. Yep, I wrote this definition, but there is no function in there, so it's under development. All right, I'm going to put this the latest version of the CLT-2021- version 3. This is still version 3. I still have to make a few more changes before I claim that I have version 4 of it. But perhaps you can try this function now in your computations for the Sahil number to see if that works for you. Does this also answer your question? Let's see, let's save this. Matthew, does this also answer your question? Okay, let's see where you are. Yes, thank you. So I have one more question. In the problem statement where it says 60m0n minus 60ms, would that be written m equals 2, n equals 2? It would be, if m and n is equal to 2, this would mean 62. No, what you're writing in the first line is not correct. The second line is correct. 60, 60. And then let's say n is equal to 3. Then you put 0, 0, 0. And then m 0, minus 60, minus 60. Then you take the symmetric of it. Yes, the second line is correct. All right, any other questions? So basically, you need to create a table. This is actually called enumeration, that you start with m equals 1, n equals 1. Then you create another row, m equals 2, n equals 1. You create another row, n equals 1, m equals 2. You create another row, m equals 2, n equals 2. And if you're still able to increase, then you go m equals 3, n equals 2. Then you do the opposite. You do n equals 3, m equals 2. And then you also have to check, all combinations of increased m and z. So it could be m equals 3, n equals 1, or m equals 1, n equals 3. Those have to be checked as well. Best way to do this, of course, is using optimization, but we'll start doing that hopefully next lecture after I finish my. Okay. So if sigma 1 over sigma 2 is negative, you need to replace xt in the third term with xt.xc. That is yes. One of them is, if both negative, then you make it compression square. But I prefer actually making this to be rather than XT square or XC. I take XT and XC here. That is correct. Do I know the difference? I haven't checked it. How big of a difference would there be, since it's the product term? But I've seen people just using XT square or XC square. If either one of them is negative, they use XC square, and if both of them are positive, they use XC square, XT square. When you say every layer, the answer is yes, but every distinct orientation layer. If you have 20 plies in there is absolutely no need to check all 20 plies. You just check the zeros and the 60s and the minus 60. There is no variation through the thickness. That's why I actually lumped all the layers together. Otherwise, you would not design a laminate like this, putting, if M is equal to 3 or 5, you don't put all 5 next to one another. But for A matrix, it makes absolutely no difference. But for D matrix, it makes a big difference. In which case, relative distribution of each of those layers is a whole lot more complicated than just lumping everything together like this. So this is, in fact, one of the things that I'm thinking. This becomes a very hard, very difficult discrete optimization problem when you start saying that the relative location of the layers make a difference. In which case, there are very few ways that you can solve this optimally. And trying the enumeration will be a horrific job, trying to find the relative location of each of those plies. I mean, even if you have very few plies, as soon as you interchange the location of one ply, you're going to make a big difference in the D matrix. Whereas the A matrix is independent of the relative location of a ply through the thickness. That's why we are lumping in the homework problem, like the way we did here, saying that 60 M, but I'm keeping a balanced laminate by using this as an M. I could have actually made 3 variables, M and say O, where O is the number of minus 60 layers. That will spoil the balance condition. And with the shear, it will make the problem even more interesting. But I didn't want to make any more complicated than this, because even the enumerating 3 variables can become a major task. So we used only 2 layers so that you can start checking M and N every combination as you increase the thickness of the laminate. All right. Any more questions on this? Other than these, how are things progressing? If you have any problems, send me a copy of your Mathematica file, and I can look at it and be able to respond to you fairly quickly. If not, we are going to continue with last piece of continuation of what we've started, which is now looking at the bending stiffness matrix as an overall laminate bending stiffness. Questions? Any more questions Do you want us to do the problem with? Yes. If you want, I can give you another day. But yeah, it looks like 100. I'll still have to check that. As I said, I did not solve this problem myself, but I will start doing so. If you want to send your file as a starting point, that'll be fine with me. I could be using it as grading it as well. Okay, so everybody okay with giving a one-day extension to this? Was it due tonight? Okay, so it will come for tomorrow. Give me heads up on these kinds of things earlier. Give me heads up earlier. Let me put the mathematical file in there so that you can also start checking my program for Sahil numbers. And then if you have any ideas, let me see what I've done on that. Yeah, hold on a second. Where I am, the Sahil developments. So this is a plot that I was doing. And this plot is, I think, incorrect for equals 1. So this is, yeah, this plot is incorrect because I need to now be able to change. So this very smooth ellipse centered at x has sigma 1 and sigma 2, 0, 0 will become a different shape. So the graphics is not working. All right, that is for sure. This is actually with sigma 1, sigma 2, and tau 1, 2 space. So it's actually a three-dimensional object. This is the Sahil surface in 3D. So there's sigma 1, sigma 2, and tau 1, 2 in here. And I was trying to make this with these x's, and if somebody wants to help me to develop this to a call that you can simply call with your stress state, and then we'll put your point as well in there. That'll be great. But this is something that I'll have to do myself. Incidentally, I have not taught the initial course on CLP. I don't think I've taught that course before. So what I'm doing with you guys, you're giving me an incentive to actually develop programs for this initial CLT programs that I think will be very useful for teaching the 585 instead of the 785 course. So these are basically some of the 585, but of course we are going to be able to use them for design. All right, so don't save this, and I'm going to go to my content, course, content module, programs, version 1, version 2. Oh, the version 3 doesn't even exist there. Okay. So, files. What did we call those things? I think I called it version 3, composite program version 3. Browse local files, composites. 3 of the program is there now, and this version has the Sahil evaluation of the Sahil value. And if I have the time, I will also check and make a comparison to find a more conservative approach, whether in the Sigma 1, Sigma 2 product, it'll be more conservative to use XT square or XC square or XT XC combination. I was using personally XT XC combination, but I've seen other people do. Maybe they're not showing, maybe they're. These are topics that when you're writing a book, you make a reference to it in the passing, and nobody realizes actually you're changing the value of the terms in there. People do that. All right. Anything else on this? While I'm at it, I might as well change the due date. This is part 1, right? Oh, there's still the part 2 coming up. Yeah. I have to also put that one in there. What was I going to do? I'll change the due date. All right. Yep. Changed. All right. Now let's get back to, as I said, so far we are able to design a laminate. If we have done the analysis calculations and computed the laminate level deformations, and from those you can compute laminate level strains. From laminate level strains, you can compute stresses in the individual layers. Then you can compare it to Sahil or Saiwu or one of the other favorite criteria. You can design your laminates. You can also compute an effective stiffness, in-plane stiffness for the laminate EX, EY, GXY, new XY, and depending on the requirements of the laminate, you can make a plot of those quantities, a polar plot in the circumferential direction. If there are stiffness requirements that need to be met, you'll be able to design, which is the second part of this particular problem, which I will put the statement in there. Besides the meeting the stress requirements, you'll also meet stiffness requirements for the laminate. Then from that, we went into bending. And in the bending case, the first and the biggest and the only major complication is the fact that stresses in each layer with the same orientation angle are not same anymore. In the in-plane case, stresses in each layer with same orientation angle are same. But when there is bending, they will not be, because as a function of their location through the thickness, the magnitude of the stresses will change, and that will reflect themselves in the principal material direction stresses. So the design job is much more complicated, and the analysis job is complicated. But on top of it, design job is also complicated, because not only you need to find the total number of plies, M and N, like what that you have here. If M is 5, that it doesn't mean that you put all 60-degree plies together. You may actually be forced. In fact, nobody puts more than 2 layers of the same orientation angle together. So you'll have to introduce all kinds of situations where if M wants to be 6 or 7, you need to start distributing those plies through thickness by interlacing them with other orientation angles. This is a major complication. And I'm not going to do the design of that for bending with manually like the way that you're doing for the in-plane problem. It's too complicated. Now, the only missing thing is we have looked at the stresses for bending case. We're going to look at some stiffness requirements for bending case. And what I'm going to do to make this thing interesting is basically go over a study where we actually said, okay, can we find laminates that are really isotropic in bending stiffness? So this is the short lecture part. And then one of the students who was doing a PhD work 2 years ago or so actually wrote a paper on this, working with a company, doing something really neat. And I'll go through the notebook to show that study where we looked at the bending stiffness properties. That will complete the manual section. And then starting with the next lecture, we're going to start talking about optimization. How do we optimize these laminates for performance or for lightweightness, weight, and how do we introduce constraints in the design problem formulation? That will be coming up. So, but first, let's finish the bending stiffness. So let me make this also 1000 here, kilonewton, and save. All right. So the lecture on this is bending stiffness, lecture 9. And I don't know if I need to make this in the presentation format. All right. So whether we really have a B matrix or not, looking at the property of the laminate for pure bending properties, we will ignore the coupling term between bending and in-plane stretching, which is the B matrix. And there is a way to do some of this by including the influence of the B matrix, but things get rather messy for that. And we're going to keep it simple for the time being, because these are more fundamental things that once you learn these things, the others will be like, if you're really, really deep into design of composites and you're designing unsymmetric laminates, which mostly right now in industry is something that is not practiced. They hardly design laminates with B matrices unless you're doing something like whatever that was, 25 forward swept wing, where you actually had to create this different coupling terms in the wing design. So by excluding the B matrix, the bending moment resultants, these are the resultant of the sigma x, sigma y, and tau xy stresses integrated after multiplying. Got it, Alex. Thank you. After multiplying z dz, so this is the moment of the stress through the thickness integrated, giving you the mx, and then the kappas are the curvatures, which are basically in terms of second derivative of the W0 mid-plane deformation terms. And if you go through the exercise of replacing the stresses with their Q bar times terms, you come up the Ij to be z cubed minus zk minus 1 cube, which if you expand this, it will be some plus minus term for zk minus 1, and then one of them will be thickness, and it'll get more interesting. But we don't really care about it. We have a module that computes the Ij terms, and we have this kind of an expression. Now, in the elastic modulus case in plane, we did an approximation coming with the effective moduli for the laminate. We called E effective, and these were EX effective, EY effective, GXY effective, and nu XY effective. In the case of the matrix, you can do something like that by doing this. This would be incidentally DX effective. That in this case, instead of A11, A22, A12 squared divided by A22, it would be D. Instead of H here in front, in case of the effective, it was just, I think, H. We'll have H cubed over 12 for the effective, but we're not going to really use this. We're going to do something a little bit more interesting than that. And that will be, we know that the D matrix is going to be changing significantly as you look at it from the different directions, 180 degrees around. What we'll do is we will define a D bar matrix, which will be integral of the D matrix around the 180 circumferential direction divided by 2 pi, the circumferential length. So this is the average of the D matrix. So D matrix is not a one scalar term. It is actually a matrix, D bar, and this is an average bending stiffness matrix for a laminate by integrating every D quantity, integrating the D matrix around the circumference. So we're dropping the idea of, let's look at the, from one direction, let's get an A value or D value, which is a scalar for that direction, and then do computations with that and show with that. We're actually taking a more aggregate approach, that we are defining a D bar matrix for the laminate. So for one given laminate, there is one D bar matrix. It's still a matrix. It's the average of the bending stiffness matrix looking around the circumference divided by the circumferential length 2 pi. So this is the definition. So what are the D bar values? It turns out that the D bar values for this case becomes the D values divided by the scalar multiplication numbers divided by some 8. These will be the D bar values. Okay, so given the D matrix, if you put those values in here, so each of these equations is different. For D11 it's different, D12 term it's different, D16 term is different. And we're also ignoring the D16, D26 terms, which is the bending twisting coupling, which is also problematic for many engineering design problems, and defining this D bar matrix. Then once we have the D bar matrix, any given value of D matrix, we can compute the eigenvalues with respect to the average value of the D, and the minimum value of the eigenvalue will give you the degree of anisotropy compared to the isotropic. Meaning that if the laminate is isotropic, the D bar matrix is going to be actually uniform and for n equal to the D matrix, and the lambda will come out to be 1. If lambda is 1, the D matrix is isotropic. If D matrix is the lambda, if D matrix is not isotropic, if there is anisotropy in D matrix, lambda will become less than 1. And the degree of anisotropy will depend on how small this lambda is, the eigenvalue of the smallest eigenvalue of this generalized eigenvalue problem, compares to 1. The smaller the number compared to 1, more anisotropic the D matrix is for that particular laminate. So this is the approach. And this is it's conceptually difficult, but implementation-wise, it's actually not very different. Incidentally, you can do the same thing with the A matrix. You can define an A bar matrix, and you'll see that you'll get the quantities for A11 bar through A66 bar, and then you can compute the eigenvalues of the A matrix. And if the A matrix is isotropic, you'll get lambda equals 1 for this generalized eigenvalue problem that says D minus lambda D times kappa equals 0. Kappa, in this case, is never 0. Therefore, this is the definition of eigenvalue problem, matrix eigenvalue problem, that the eigenvalues will give you the condition that actually makes this condition to be satisfied. So that is the lecture part. This is the only thing that I want to talk about, and I'm gonna close this. If you have any questions, please do raise them. Questions? Okay. Then I am going to be looking at for some reason, my computer decides all by itself which camera to use. I think today it's using the camera from the lower screen, so when I'm doing the lecture, you're probably seeing my chin, which may be a better view, because otherwise you might be seeing my bald spots in my head. Not that my chin is any better looking these days. All right, so let me close this and get my tutorial. $200 is a good magnification. All right, so I don't know if this is working anymore. If you do this, it used to actually print anything that's matrix in matrix form. But let me check what happened to this dollar preprint. Dollar preprint is a global variable whose value, if set, is applied to every expression before it is printed. So it is supposed to be working. And I say if matrix Q, number 1, matrix form, yes, it is matrix form, and number 1 comes from here, and this is applied to, I made a pure function applied to that. I don't know, let's check if 165, 169, 165. Good. All right. Let me execute my program. This is run code. All right. And let's see if any function there is available. Yes. And Sahil failure is there, but plot Sahil failure is not working yet. All right. So the first thing that I did, which is not in the program, is to write this function bar matrix. And if you remember the equation, it had 1 over 8 times A1, 3 times A11, 3 times A22, 2 times A12, or if it's the D matrix, D11, D22 to add these terms. So this is a 6 by 6 matrix repeated here. This equation here completely duplicates this, not this one. These equations here, D11, 12, S66, and it's 3 times A, 3 times D, 2 times A, or D, 4 times D. Okay, so basically these 4 equations are coded into this function called bar matrix. It can do either A matrix or D matrix. Let's define the D matrix as matrix D to be D11, D2, D66, but it doesn't matter if you ignore D16 and D26. Bar matrix, I can take this matrix and do the this, and you get this thing here. And if you do percent, matrix form. Oops. Let me do one more time. Not percent, matrix form. Percent slash matrix. Or I could have done the matrix form, open bracket, percent, close bracket. So you can see that bar 6, 1, 6, and 2, 6 are already 0. And this is basically the bar matrix, which is integral of the D matrix around the circumferential direction. From there, we're going to go to the eigenvalue problem. So for this demonstration, we're going to use an interesting concept. But let me first define material properties. E1 is this, E2, nu12, G12 are here. Layer of thickness is 0.093 10 to the minus 3. U vector is invariant U of these quantities. Okay. And if I execute this, I get all the material properties. So my material properties are ready. This is a material, actually, we're going to treat a combination of 3 layers as 1 layer. And the reason for it is, for this study, we worked with a company that was producing what's called a laminate out of 3 very thin plies. These are put together by doing stitching, non-crimped fabric. These are stitched 3 plies on top of one another, and they were stitching these 3 plies, zeros, plus minus 30s and 90s, to make one fabric, which is quasi-isotropic. Okay, and they were planning to market this product in the United States, and they're saying that, hey, if you buy our material, you don't have to worry about these different ply orientation angles. What we're selling you is a quasi-isotropic fabric, and it's a combination of the plus minus 30s and 90s, and they made it to be actually in this form. So this is literally how they stitched them together. So this QI plus is 3 layers, very thin layers. So when they stitch it, it's almost like 1 layer of a regular material, but it's quasi-isotropic and it's made of plus 30 slash 90 slash minus 30. And they want to sell this. But one thing that you don't notice, and it's going to take some time for you to really appreciate it, if you want to make this to be symmetric laminate, you don't take this 3-layer quasi-isotropic, which is plus 30 minus 90 minus 30. flip it around and put it on top of the previous QI, that also gives the same orientation angle, plus 30, 90, minus 30. To be able to do symmetric, mid-plane symmetric laminates, you have to create another fabric from your plant, which we will call QI minus. And that layup is also quasi-isotropic, but it has minus 30, 90, plus 30. Okay? And when you put these things together, then you get a quasi-isotropic laminate with two layers of their fabric. In terms of distinct orientation, there are 6 layers. Plus 30, 90. So if I run this to make a really QI, I need to join them. I forgot how join works, but let me try and see if it works. Yeah, plus 30, 90, minus 30, minus 30, 90, plus 30. Otherwise, you cannot get a quasi-isotropic layup. So when we ask them, okay, you're going to try to sell this product claiming that you're always getting quasi-isotropic properties, what about bending properties? I said that'll be interesting to look at. So how isotropic is actually the bending properties of this. Now the neat thing is, when you take this 3-ply, each of this darker layup that you see is one of these, plus minus 30, 90, minus 30. And this is QI minus. So if you rotate these around this z-axis, the in-plane properties of this is isotropic, in-plane properties of this isotropic. So whether you turn this ply in that direction or you keep this, it doesn't make any difference. In-plane properties remain isotropic. But if you look at the bending properties, you're going to see that when you take two of these together, you rotate the top one by an angle phi, you're actually also changing the bending stiffness matrix of this. So first, we're going to look at the bending property of one single QI plus or QI minus. And then we're going to look at this, but after actually changing the QI with a phi, and I think we're going to put a minus phi in there to be able to orient this different directions, or plus phi, to see how that will change the D matrix. It will not change the A matrix. Okay? So this is what we're doing. So let's look at the A matrix. If I do the A matrix of the QI plus, and then do the A bar matrix, and look at the eigenvalue of these two eigenvalues of two matrices give you generalized eigenvalue. So let me put the question mark. Eigenvalues is a mathematical command. If you give a matrix M, gives the list of eigenvalues of the square matrix M. M has to be square. If you give eigenvalues M, comma A, gives the generalized eigenvalues of M with respect to A. Both A and M are matrices, so this gives the generalized second line of the M matrix M with respect to A. This gives the first k eigenvalues of M. That's a scalar value, that it's 1, 2, or 5. And this is the generalized eigenvalue, first k values of the generalized eigenvalue. So generalized eigenvalue is A, comma, A bar. So I'm going to call this A mat 1 with the QI plus, then compute the bar matrix, A bar matrix, and find the eigenvalues of it, and take the last eigenvalue, which is the smallest. So actually, if you want, I can also do 3 lines in here. First show all eigenvalues, and then the last eigenvalue. So let me execute this line. So the A matrix is this. As you can see, there's A11 here. A22 is here, is equal, so it's quasi-isotropic. And then all eigenvalues are 1, meaning that it doesn't matter whether you take the smallest one or the biggest one. The smallest eigenvalue is equal to 1. All right. The A2 is my QI minus. This is the 3-ply with the minus layup. This is this one. It starts with minus. And if I execute this one, again, identical, all right? And in fact, if I looked at the QI, which is joining of the 2, that will also be exactly the same as these. All right. Now, let's not do that. Let's not overkill. If you want, you can basically copy this and make this QI. I'm making a new label out of it, but still, it's going to be same properties. All right, A matrix is larger because it's twice as thick, but it's basically twice as thick as this because I combined 2 sublaminates of 3 plies. So total laminate now is 6 plies thick. That's why the A matrix changed, but it's still isotropic. As you can see, A11 is equal to A22 here. And eigenvalues, all eigenvalues are equal to 1. All right, D matrix. This is QI plus. And I'm taking the D matrix and looking at the eigenvalues. And I see that the lowest eigenvalue is 0.266. Quite low. In order to be isotropic, the D matrix of this QI plus. And same as the QI minus. Now, curiosity, do you think the 6-ply layup is any better or any worse than this? So I'm going to do the QI. I'm going to make this 3. Make this also 3. Make this 3. Make this 3. Make this 3. I hope I didn't forget. Different D matrix. Same degree of anisotropy. All right. So I don't need to do this. Why am I doing this? I am actually looking at the polar moduli again. I don't have to do these. I'm going to delete this line A and B matrices because we saw that they are same. The A matrix, B matrix, A matrix bar last eigenvalue. This is the same line that we've done before. Effective moduli. I can do the effective moduli of this layup. This is EX, EY, GXY, new XY. You see EX and EY are same. The polar moduli of QI plus is basically a constant. A small circle, because I think this is kept as 6. I think I need to do something in this module so that I can scale this. And for in plane, I think this should have been, the largest should have been 1 instead of 6. So that you can see that this is actually quite small compared to E1. And it's probably 0.2. This is the shear, which is the third value, and this is the fourth value, which is new. So let's go to D bar matrix. This is the bar matrix. Again, for the QI plus small eigenvalue. We've done this line already, 0.266. And they compare the isotropic D matrix and the D bar matrix. They are the same. Then why am I doing this? Oh, I'm gonna actually do different orientation by around 360 degrees by putting a degree 1 through 360 to the QI plus. Okay, so I'm going to rotate the QI plus by some angle from 1 to 360, and I'm going to compare them together. This is going to do all of those layups. So this is actually laminates with all of those different orientation angles. And if I do the D matrix calculation, all of them come out to be 0.266, and I can make a polar plot of this, which is now 0.266 with a radius of 1. This didn't use the module that I have, but it actually plotted every one of these angles in there. So now I'm going to take 2 layers of what I call Q tape, and I'm joining them and flattening them. This is actually what I did by creating, tape 1, tape 2 now. QI plus, QI minus. So 30, 90, minus 30, minus 30, 90, 30. Then I'm going to take QI plus here and QI minus, but I'm going to rotate QI minus by a small angle. So what I'm doing basically, if you remember the figure top below, above, QI is the layer on top, QI minus is the layer at the bottom. I am rotating the QI minus by an angle phi from x-axis. So I'm keeping the top layer the same, QI plus, but I'm rotating QI minus by an angle phi compared to this. This is not going to change the A matrix, but it's going to change the D matrix. And I want to see what it does to the D matrix. All right. Where was looks like here. Symmetric laminate configuration, but the bottom layup is going to be rotated by this angle. It does all of those here. So this is now the layup. The first layup is 3090 minus 30 minus 3090 30. Second layup is 3090 minus 30, but the unsymmetric part of it minus 29 91 31. Every orientation layer is shifted by 1 degree. And then I'm going to take the D matrix of all of these above, then integrate them, find the circumferential D bar matrix from that, and compute the smallest eigenvalue for each of those. And that will be these. As you can see, the degree of anisotropy was 0.266. As you're rotating, it starts increasing. 2667, 267, 268, and it's growing actually, 0.4. So now I can look at the position of the smallest EV as 299, and this is the maximum, this is the minimum, 361. Base laminate for position 299 is this, and best laminate for the position flatten, minus flatten, tape 1, tape 2, QI plus for this, QI minus. I rename tape 1, tape 2 as this, and that will be the best laminate QI plus best laminate this minus the QI plus minus QI minus. That's 298, 298, 298. I don't know if I typed something incorrect here, but we'll see. And the D matrix for the best laminate is this. This is the bar matrix for it, and the eigenvalues for it. And the value it reached is 0.54. Reverse laminate is the other one, and it's this one. And the smallest value for that is 0.266. So it didn't go anywhere. So I'm going to show all of those now in one plot. And this is what you see. So what this plot is showing is the D matrix degree of anisotropy. This is not the, this is the degree of anisotropy. So for Q plus slash Q minus plus theta, where theta phi, not theta, phi is changing from 0 to 360, the degree of anisotropy was 0.26 for this layup, and it reaches a value of 0.5 something for either this value here or this value here or this value here somewhere, and that value is 0.54 and reaches at the phi value of it's kind of symmetric. It repeats itself 4 times. So you'll see that 0.54 4 times. I think it's around somewhere in here. I should probably put a point in there. So as you can see, if I take 2 layers of quasi-isotropic, put them on top of one another, I can actually improve the D matrix isotropy for some value of the speed. Now I'm going to take 3 of these QI tapes. Tape 1, tape 1, tape 2, tape 2. I'm sorry, 4 layers. And I'm going to rename these. Let me do something. Copy. Find. Oops, not find. Not there. Not that. Oh, come on. All right. But I don't have to change every time. So I'm going to take 2 of these QI pluses and 2 of the QI minuses. And I'm going to create a laminate called 3Q1. So 3090 minus 30, 3090 minus 30, minus 3090, 30, minus 3090, 30. So mid-plane symmetric still. 2 of the layers, 2 of the layers. I'm going to create laminate LAMS 4 plot. I don't know why I call it LAMS 4 plot. And of this. But I'm going to take QI plus and then QI plus J. So I'm rotating one of the QI pluses and also rotating the QI minus with the same amount and creating this QI minus. So this is another strange combination. So I'm changing. Let me see if I have a figure of this this particular construction. If I do, I think I may want to put that in there. I don't have a figure for that laminate. But it can be made. Basically, it is something similar to this figure above, except there are 2 of these QI pluses, and then there are there are 2 of QI minuses, and the layers close to mid-plane is rotated by a phi degree, both for the QI plus and for the QI minus. Oh, we are over time, gentlemen. You're not stopping me. You need to stop me. I can go on for forever. Very quickly. That's what it is. And these are the layups, 364 of them. And if I make a computation of all of those and compute the indices for lambdas, and the best laminate is this one, and it corresponds to this 3090 minus 30 minus 30 3090. You can see that actually second QI is rotated quite a bit compared to the first QI. QI plus. So that's the best, that's the worst. This is the worst laminet. This is the eigenvalues of the highest is now 0.81. Very substantial increase. This is the D matrix, and you can see D11 is getting close to D22 here, 5.5, 6.5. This is the bar matrix, and this shows the plot. As you can see, although it's not completely circle, this layup here is much better than the two of them. Rotate. So mid-planes are rotated. You can go to 6 by doing 3 of these and 3 of these, and you will see all kinds of interesting things. I'm going to send the paper for this and send a notebook, and you'll be able to run all the cases shown in the paper with this tutorial. That I'm going to have to stop. I should have stopped 10 minutes ago, but now I'm coming to a hard stop. I apologize for keeping you guys so long. All 9 of you are there, I can see. If you have no questions,